All right, and with that, just a quick shameless plug here as always. Chris and I, we also co-authored a book if you're interested to learn more specifically how to run data science on AWS. There's an O'Reilly book out there. And in our meetups, we focus on different topics and always invite exciting speakers here as well. And today, I'll just switch over here to the meetup side. We do have a great lineup. In just a second, I'll hand it over to Francesco Pochetti, who is an ML engineer working on computer vision and is also an AWS ML hero. And Francesco will talk about how to blur faces. And he's using an exciting stack of technologies there that he will walk us through in a demo, how to train, optimize, and deploy a segmentation model using Amazon SageMaker with NVIDIA TensorRT and NVIDIA Triton. So super excited to hear that talk here in just a bit. And then we do have a second set of speakers here joining us today, Joe Evans and Daiming Yang, both from AWS, engineering manager and software engineer. And they will show you PyTorch's new native integration with S3 for really fast data loading. So also excited to see a demo there. And with that, I'll stop my screen share. Quick housekeeping before I hand it over here to Francesco. Please put all of the questions you have along the line here for our speakers, anything in the chat window, and switch the little to everyone so we can see the questions, and then we'll answer them as we go along. And of course, after each session. So with that, no further ado, Francesco, take it away.
Thank you. Do you guys see my screen? Can you hear me well? Everything is good?
Yes, we can see you and we can see the screen too.
That is great. Okay. Hello, everybody. Thanks a lot. Thanks a lot for being here. Like, great to be here. Thanks for inviting me. And super glad to be talking to you today about how to train and deploy a segmentation model to blur faces on Amazon SageMaker and NVIDIA Triton. Everything I'm going to discuss today is contained in this blog post of mine. So it's pretty detailed. So in case I miss anything or anything is not super clear, just please feel free to head it here. It should be covered. This post is also going to give us a skeleton of the talk today, right? Just a little bit of the agenda idea. So we're going to start with exactly what it is that we're going to build and why. Then we'll move into the training part, so finding a data set and training a model, and then of course like the deployment, right? So converting like the PyTorch model, which will be training into Torch script first, and then Onyx, TensorRT, and then moving into NVIDIA Triton and SageMaker. All right, so what is it that we're going to build today? And in order to show you that, I guess the best way is to head over here into this Hugging Face space, which I created, which is hosting like the Torch script model we're going to train in a bit. The idea here is that we're going to feed an image like this with people, and the model is going to detect where the faces are, is going to identify them and blur them like this. Like this, there you go, like this, right? So faces are going to be detected and blurred. This is what we're going to build, right? This is the model where we're going to train and then deploy. All right. So why are we doing this, right? Well, because it's fun as a starter, I would say. And then most importantly, because at least like myself, I thought that it would be a pretty clear ethical application of AI. Ethics should always be like a top concern, like when building machine learning systems. I feel that it's not always the case, unfortunately. Yet I think that the community has been doing like a great amount of progress and work in the last years. There is still a lot to do. So I thought, well, what about leading by example and picking a side project, having ethics and AI together, wrapped up together. And I told myself, well, what is like? Is there anything more potentially impactful than advocating for people's privacy and then automatically blurring faces in a crowd? This is basically everything, how everything started. And so I got like this idea, like put it on my like to-do list, and stayed there for a while up until the CEO of Hugging Face tweeted this, right? So idea for positive use case of face detection, an Instagram filter to automatically blur all faces when you post a picture of a crowd. You know, I read this and I was like, okay, there you go. That's kind of, you know, the little push which I needed. That's you know, like let's go and do this, right? So I started with pre-trained models from face detection and cornea, which are two pretty great computer vision libraries offering like all sorts of algos, like pre-trained algos. And the idea there was that, you know, to feed like the input image into a model which would detect just faces, like, you know, just bounding boxes, and then blur the region inside the bounding box, right? So the output would be something like this. I mean, was something like this, right? So input image and then output. And so as you can see, this is like very, very accurate, but also like very, very ugly, at least for myself. So when I look at that, I was like, okay, like no way it's just gonna be like that. There must be something like more, you know, nicer I can do. And that's where, you know, semantic segmentation, like the seed of semantic segmentation started like growing like in my head. So for the ones who are not familiar, semantic segmentation is the branch of computer vision which consists in looking at every single pixel in an image and classifying it, right? So basically, in my case, we would be looking at every single pixel and classify them as either background or face, right? That's it, right? So, and then like the idea is, well, you know, the moment like we get which pixels belong to the face, that we can just blur them, and we won't have all these like, you know, sharp edges which are, you know, super ugly in a rectangle or a square as we saw before. All right, but we don't have any pre-trained models for that, so we gotta train them, right? And that means that we can go and you know, check out some code. All right, so okay, first things first. What you're looking at right now is a VS Code session, which is running on top of a Docker container inside an EC2 machine. So the EC2 part is not critical, I would say. So you can run this thing wherever you want. The Docker is instead, in the sense that, you know, we'll see later on exactly, you know, which kind of, I mean, which exact command will be cause for trouble. But, you know, you have to, you know, keep in mind that we are basically using, you know, several libraries which have to, you know, play nicely together, namely TensorRT, and it's not always super easy, you know, to get it done. So unless you want to get into a land of tears and pain, which I hope you don't want to, just use Docker. I honestly, you know, I tried it myself to install everything like on Ubuntu. Didn't really work out. At some point, I just opened an issue on NVIDIA forums, and they told me, dude, I mean, just use Docker. And I told them, yes, I mean, you're right, goodbye. So now we are on Docker, works very well, and I won't look back. All right, so whenever we mention a model, we mean data, right? So there's no model without data. So in this case, we need a data set with faces and segmentation masks. And for that, I looked into face synthetics, which, as the name suggests, is a data set of entirely synthetic images from Microsoft. It's a great data set, which is constituted of 100,000 images of 512 times 512 pixels resolution. They're entirely synthetic, right? They show like human faces from, you know, all sorts of you know, background, gender, race, age, and then clothing, lighting conditions. It's awesome, right? And they're coming with a bunch of, you know, segmentation masks. As you can see, there are lots of them, right? There is, you know, not only face and background. There is, you know, face, background, nose, ears, eyes, glasses, everything, right? So in my case, I don't need all of that. I just need a background and face. So the very first thing I do when loading this data is to actually convert them into binary masks, right? So they're just two classes, either background or face. And this is what like it renders, right? This is how it renders. So we are using Ice Vision, which is an awesome library for, you know, training to train the model. It's a library which offers both object detection and segmentation, both like semantic and instant segmentation. We are doing semantic segmentation here. But yeah, so it's pretty cool. So the idea, I'm gonna go through like the training part pretty fast. I think that it's probably like we could be talking about this for the next couple of hours, and I don't think we want that. So we're gonna probably like get into like the deployment part a little bit faster. But anyway, so in a nutshell, what happens here is that I'm loading this data set. Actually, I'm getting a sample of 1,000 images out of the around 1,000. I'm loading them into records, which are the kind of the building blocks of Ice Vision, and then defining, transforms and data sets, data loaders, which are just some fancy. These are like the result, the results of augmentations, by the way. Anyway, so data sets, data loaders, which are just some fancy words to say that you have a list of images, gotta iterate over them pretty much. And then we define the model, which is UNet with a ResNet 34 backbone. So that's pretty standard architecture for semantic segmentation. It's there are like newer architectures, fancier architectures. This works really well. It's fast. It does the job. And ResNet 34, which has been pre-trained on ImageNet. All right, so batch size of 16 and resizing to 384, just to make sure that everything like fits on the GPU, fits on the GPU, and then defining my accuracy. And training the model. There you go, right? So I'm training for 30 epochs, and actually I could have stopped at the first one because I'm getting like 97% accuracy already, like on the first epoch. I mean, the validation loss, as you can see, like dropped dramatically by pretty much an order of magnitude, but accuracy doesn't really change. So we are probably just fiddling around with pixels around like the edges, right? So the model knows how a face looks like. That's kind of what this tells us. We train it, and then we are like, okay, how does the model performs, right? And the best way to do that is to show a comparison, right? So this is the ground truth on the right, on the left, and then the prediction on the right from the model. So as you can see, it's pretty much spot on, right? Well, I mean, it's not crazy accurate. So like the hair here is not like detected very well. But for our purpose, which is detecting the face and then blurring it, I think it's fine. And honestly, this is a work which costed me 40 minutes, and as I said, I could have stopped probably after 1 minute and 36, considering the accuracy. Okay, now I hear what you're saying. Okay, dude, I mean, this is like this validation set looks exactly the same as the test set. How about like an image where you have multiple faces? How does this look like? And I asked myself the same question, and here's the results, right? So this is that exact same model which we looked at before, which is predicting on more faces. It's not, okay, I have to admit, it's not like that great, but it does the job, and this is like the result for blurring. Like I think it's okay, honestly, like for a first MVP, which is happening, which has been trained in 30 minutes. It's more than enough. All right, so we got our model. It has been trained. It is a pure PyTorch model, so no optimization happening in here for the time being. Let's move to how do we want to use this thing? Antje, are there like people raising hands?
Yeah, just a quick reminder for everyone who has questions, please put them in the chat and then we'll get to them. Yeah.
Okay, great. All right, okay, so what do we have here? We have a model which has been trained on on this data set from Microsoft. Everything, life is good. PyTorch. Now, how do we use this, right? Alrighty, so there you go. So let's move on. So here's the thing, right? So we want to deploy our model to TensorRT and then Triton and then SageMaker. So we know it's going to be crazy fast, right? This is great, but then like I think it's important to always have some sort of baseline, right? A benchmark, at least, like to know exactly what we are comparing our model on. I mean, our model like to, so that we know exactly how fast our model is going to be. And so that's why I am going through the trouble of converting this model, this PyTorch model, into Torch script. So this is not an entirely necessary step. I could have gone with the pure PyTorch. Like Torch script is just a lot easier to deploy because I just need Torch as a dependency. So in a nutshell, here nothing interesting is happening. I'm just saving. Where is it? Oh, there you go. I'm just, there you go. I'm just saving like the tracing and then saving like the Torch scripted model. For that to happen, I need to provide, well, of course, the model and then a dummy input. We could talk for at least a couple of hours about the input resolution. Technically, it can be any size. This is like yes and no, depends on the architecture, depends on the framework. I'm gonna stick to 512 times 512 for the entire session. But my suggestion, just try whatever works for you and stick to the resolution which works. Alrighty, so we got like our model which has been converted to Torch script. This is great. We're gonna park the model here, and then we're gonna get back to it later on. For the ones who are wondering what is Torch script, it's just the optimized version of PyTorch, pretty much, right? So what this does in the backend is that it kind of like runs the dummy input like inside the model in a forward pass, and then figures out like the computational graph, and then it kind of optimizes it, right? Alrighty, so there you go. So we got our model. It's in PyTorch. PyTorch Torch script. I'm also actually checking if everything is fine. I'm kind of visualizing like the mask on top of the prediction from Torch script here, just to make sure I didn't screw anything up. I'm also like comparing like the outputs from the original PyTorch model with the Torch script version, just to make sure once again they didn't screw anything up. The outputs should be the same ideally. Okay, so we're good. All right, so now we gotta embark into our journey to TensorRT, right? TensorRT and Triton. And the very first step is Onyx. So we gotta convert our PyTorch model into Onyx. So Onyx, for the ones who are not familiar, is a framework which I think was developed by Microsoft originally, and it's a framework agnostic tool which allows to convert models into some sort of like optimized engine, which is definitely faster than the original model, and most importantly, it doesn't rely on any other dependency other than Onyx runtime to run. So it's pretty great. And the export like to Onyx works in very similar way to what we did for Torch script, right? So we are using like torch.onyx.export. We are passing the model. We are passing a dummy input. So just to let know Onyx exactly which kind of input dimensions it needs to expect. For Onyx, there is dynamic bed, dynamic axis, which we can actually I am fixing here. Kind of works, kind of doesn't work, not all the time. We can get there in the Q&A if you guys are interested. But anyway, so long story short, we convert it to Onyx, and then we check if everything is fine. We have like a very nice utility from onyx.checker.check model. Everything is great, all is good, and then we go through pretty much the same process we did for Torch script. So I am running here like the inference, right? As you can see, it's literally one line of code. So everything is based on top of the Onyx runtime. Loading the model, running it, and then I get a list here, and I'm checking whether where is it? First, I'm checking that the masks are fine, and they are just with this little visualize mask function. So everything is good. We didn't recover the entire, the exact mask that we got from Torch script and PyTorch. Here they're matching at 99%, but it's fine. Honestly, I'm just looking at the visuals, and the visuals look good to me. So I know that they didn't screw anything up. But I always check, like that everything is fine. Also in terms of like pixel wise comparison. Something to note is that here Onyx is running on one average on 1.4 seconds, right? And you might say, okay, is this good or not? Actually, it's pretty good compared to the original. There we go. So the original Torch script, both original PyTorch model and Torch script, which were both running at around like 2.1 seconds on average. So it's already like a 30% increase right off the bat, like just converting like from PyTorch to Onyx, which is pretty good, like, to keep in mind. So like, long story short, honestly, if I had to stop here, if you want to optimize something, just go for Onyx as a first choice, because it works like pretty well. Alrighty, so we got Onyx done. Now, okay, now we had like everything we need like to convert to TensorRT. So what is TensorRT? So TensorRT is two things. It's an inference compiler and a runtime engine. So by compiling your model with TensorRT, you're pretty much 100% guaranteed having decrease in latency and increase in throughput. So like the performance is going to increase, and that what happens under the hood is that there's a bunch of optimizations which are generally around layers fusion in the model. So like TensorRT looks at like layers which can be like fused together, like to optimize like the operations. And then there is another thing which is quantization, right? So the weights which are coming out of the training, which are generally in FP, so like single precision training, or could also be half precision, so FP 16. But you can like decide to quantize even more. In this case, for instance, as you can see, I am going for int 8, so like literally like all the way down to the most aggressive quantization possible. And I'm also like specifying which by the way, to keep in mind, generally comes at a cost of accuracy, right? So you're gonna increase dramatically your performance in terms of latency, but then you're going to lose on accuracy. In my case, amazingly enough, this doesn't happen. And I think that even honestly, it might happen for a couple of pixels here and there, but I don't care. The result, which we're going to see, is this pretty much. Like visuals are fine, which is what I care about. And this is amazing, right? So this is literally the command. This is the reason we're using Docker, right? At this point, that's where you're gonna start crying if you didn't use Docker, because that's the point where everything is gonna fall apart. So use Docker, please, and this command is gonna run like fine, and the output is gonna be model.plan. There we go. Like, see this guy here, model.plan. That's the output of our TensorRT exec command. So we got our TensorRT model. So it's optimized, even more optimized than Onyx. Now we can go to the fun stuff, which is deployment. Alrighty. So okay. So as I said, I didn't want to go like immediately like to TensorRT and Triton and blah blah blah. I wanted to have a baseline, all right? So that's the reason why we converted the original PyTorch model to Torch script to have this kind of baseline. And so the very first endpoint which I deployed is just around. Oh, there we go. That's the one. It's just deploying the the PyTorch model. PyTorch, sorry, the Torch script model. All right, and it's insanely easy, honestly. So let's look at the serving code here, because you probably won't believe it. Where is it? Torch script. There you go. Serve.py. That literally that's it, right? That's the code which you need to run a Torch script model, right? So you import Torch here, and then you're basically just loading the weights, and then loading the weights here, line 6, and then you are just running the model right on top of the input image. That's it, right? Half of those lines are print statements. So it's what, like, it's probably like 7 lines of code, right? Easy peasy. So that's why I went like for Torch script. I didn't want like for the original PyTorch model. But yeah, so like I have, so we can try this out, and this is like the input size, like the input image, right? And then I'm going to I can instantiate a model. No, it's not instantiate the model. Like instantiate like the predictor. So calling like the endpoint, and then I gonna predict and everything. And there you go. And that's the output. So the output is just to figure this out, is 2 times 412 times 412, just because So we have 512 times 512 pixels, like, you know, and for every single one of those pixels, the model outputs 2 probabilities, right? A probability of being background or being face, right? So that's why we have 2 numbers per pixel, right? This is like the reason why we're having like this kind of output. Anyway, so I'm also, what I can do is that I can load you know, the original Torch script model, which I have like locally. This is running locally, and then I can check if you know, they match, and they match 100%, right? Which is great. Like that's the output from SageMaker matches the output from you know, like locally, which, you know, should be the case. Anyway, so here we have like our baseline. Now Triton. Alrighty, so TensorRT, once again, we got our model. We got our model plan. So let's close this up. We have our model plan, which was converted using TensorXec. Now, how do we tell SageMaker to deploy this thing? And how do we use Triton? So first, we can use, I'm gonna get in a second into Triton. So we can use Triton seamlessly on SageMaker because the teams at AWS and NVIDIA are awesome, and they you know, they kind of like figured out the backend for us. So you basically upload a model artifact, right? And you basically tell SageMaker, hey, dude, I mean, I want you to use Triton, pretty much. And then, you know, AWS does the magic, right? Otherwise, so making sure that Triton gets deployed like inside like, you know, the SageMaker endpoint. For the ones who are using, like, who are wondering what Triton is, it's an inference server which was developed by NVIDIA, and it's, you know, crazy optimized, right? It's a super optimized engine, inference server, which in terms of like the big difference with the other ones, like, you know, Torch server, which are available out there, I think that the biggest difference is that like it works really well with NVIDIA architecture, first of all, and then also like it makes sure that the hardware utilization is always as high as possible, right? So it like it's pretty much guaranteed like to have like a big speed up in terms of both latency and throughput. And it also ships with all the kind of magic which you can come up with, which is like your dynamic batching, concurrency, pipelines, executing pipelines or like multiple models at the same time. It's pretty awesome. Anyway, so the deployment here happens. Where is it? No, I'm just. Oh, there you go. That's the deployment part. I hit it. So the deployment here happens with as usual. So we got like a package, like a model into a part.gz, and the contents of this package are. Here, where you go? There you go. So they are the model plan, right? That's the one we created with TensorRT, and most importantly, there is this config file, which is basically, you know, a recipe for Triton. I mean, to let Triton know what it needs to do, right? So, you know, the input images, output images, input, output resolutions, model warm up. You know, do I want to use like one GPU more? Do I want to use concurrency? You get the point, right? That's the kind of, you know, the recipe to tell Triton what to do. And then, you know, when you got like this package, I mean this you know, tar.gz packed up, then we can upload it to you know, we're gonna upload it to S3, and then go ahead with the standard way of creating a model, which is literally creating the model, creating the endpoint config. If you're familiar with, you know, with the Boto3 Amazon, I mean, it's SageMaker SDK, endpoint config, and then creating the endpoint, and the result is this, right? So we have 2 endpoints up and running, right? So that's the one from Triton here, and then the one from, you know, IceMask, I mean, the Torch script over there. And what we can do is that we can just invoke them, right? So actually, you know, I can invoke like once. Oh, okay, I really hope it's gonna work. All right, bam, there you go. So yeah, I just invoked. I just invoked like the, where is it? Invoke endpoints. I'm not cheating, right? I just executed this. You saw it, right? So I'm invoking the endpoint, and I'm getting the expected output. I can actually check in here that the mask is what I expect. So I'm plotting the output from the TensorRT and Triton, and it is working, and life is good, and I'm a happy man. Okay, here you guys. If we're talking for around like 30 minutes already, show us some numbers, and that's what I want to do. That's what I intend doing right now. So here it is. I'm not going to. Oh, actually, yeah, but let's do that anyway. So we're gonna time it. So I'm just running, this is like the Torch script endpoint, right? This is running like 197 milliseconds, right, on average. This is inside the notebook, right? And now we can do the same with Triton. So we could, as you saw before, we are like at what, like 80, 87. We're gonna get to 89, right? So 89 milliseconds. So that's already like more than 2x. And this is happening inside the notebook, right? So we have all the network overhead, converting the inputs, outputs, blah blah blah. So I think that something more interesting would be to actually go and check inside the CloudWatch, right? So let me refresh this thing. Okay, there we go. So this is like the actual model latency from CloudWatch, right? And for Torch script, so here it is, Torch script. It's 127 milliseconds, right? So that's literally the execution on SageMaker. And when I go here, bam, there you go. It's 15 milliseconds, which is absolutely mind-blowing. And this is TensorRT plus Triton plus SageMaker, which makes up happy life. And that's pretty much it, right? So it's what, like 8x? I think it's 8x speed up. Yes, 8x. So we got an 8x speed up, which is pretty amazing. And once again, I mean, I could keep talking for the next couple of days. So I guess Antje, it's probably on you, and we'll figure something out for the questions. Thanks a lot, everybody.
Thanks so much, Francesco. Wow. Yeah, that's a lot of work you put into this demo. Thanks so much for that and sharing here. Quick reminder, everyone, and a quick apology in the beginning of the meeting. Zoom had changed their security settings, so the chat was disabled by default, which I just figured a couple of minutes later. But it should work for everyone, hopefully, now to put in, if you want to put in more questions. We did have a question coming in, Francesco. Are the inference times based on CPU inference?
Oh, no, they're running on GPU. Good point. Yeah, like both. Both. Where is it? Both endpoints are running on yeah, there you go. They're running on GPU. And this is like Torch script and sorry, this is Torch script. Sorry, this is TensorRT and Triton, and which is running on GPU, and this guy here is also running on GPU, and that's Torch script.
Okay, cool. Yeah, and just for curiosity, so in the beginning you showed those square blur approaches, right? Is this one now, is it just about the accuracy? Is it faster? Is it better? So just maybe to put it in context.
You mean like this guy here, like the Oh, yeah. No, they were just very ugly, honestly. I mean, like the only reason I could have this took me like this is literally 5 lines of code. So Cornea was like blazing fast. So you should probably go with Cornea, like if you want this thing. But I didn't want it, honestly. I saw it, I was like, oh okay, no, I don't. So I want something better.
Yeah,
I mean, come on, this is better, right?
We can do better, right?
Yeah.
Okay. Okay, great, gotcha. Around the GPU usage, yeah, I think you showed which one you used, right? We had a question here, which GPU was it?
Yeah, so that's where is it? That's G4DN, so that's T4, NVIDIA T4.
All right, and how did you determine the size of the image to fit on the GPU?
You mean at inference time?
Yeah, Chris, I think yeah, you had a question.
So like for training, actually, I'm also using like G4DN for training, and that fits, like you're just try until it works, honestly, just to optimize, as much as possible your GPU usage. For inference, honestly, if given I was using the same GPU, if it was able like to stack up 16 images for 512 times 412, it was also able to stack one single image of 512 times 412 pixels resolution. So I didn't really go down the road of optimizing the image size there.
Okay, gotcha. And you mentioned a 10 times performance boost. Where is that coming from exactly? Can you pinpoint that?
8x. So that's
8x,
that's this
okay.
guy over. That's this guy here over this guy here, pretty much, right? No, so that's literally model latency as per CloudWatch. So comparing literally just the model execution per se on Amazon, I mean on the endpoint. And so this is Torch script, right? So 126 milliseconds. That's the an average of 1 minute calls, right? So and as if you remember, this is coming from this, right? This command here. So it's basically executing, like there are 7 runs, so it's executing multiple times, right? And so in this loop, this is basically a loop in which I invoke like the endpoint multiple times, right? And then this is where this is coming from, right? And then I check, the kind of latency I'm getting out of CloudWatch. And this is 126 milliseconds compared to 15.
Yeah, and is it because of TensorRT? So why do we see this improvement?
Both. It's both. It's a TensorRT and the Triton, right, at the same time.
Okay.
We could try with, like something I didn't mention about Triton is that so you actually don't need to deploy. I mean, you don't need TensorRT and the Triton at the same time, right? So you can actually just run with TensorRT as is, right, on a standard GPU, because as I said, like TensorRT is also like a runtime engine, so you can just execute with TensorRT. And NVIDIA Triton as well is an inference server, so you can also like run plain PyTorch there, right? Or scikit-learn. Like honestly, it works like pretty much out of the box for frameworks.
Okay.
So yeah.
Okay. Another question: do you have a number for inferencing using just Onyx runtime on GPU without the Triton server?
Oh no, I don't. But it would be like a nice experiment like to go for. As I said, like as we saw like on GPU. Actually, that was running on CPU, by the way. Like the 100, like when I showed you guys that we had like 1.4 seconds. Where was it? Here, right? So 1.4 seconds versus 2 seconds. So that was running on CPU and inside the notebook, right? And that already like shows that Onyx is it's pretty fast, right, by default, by itself, without doing anything much.
Yeah.
So,
okay.
Yeah.
Great. How about cost effectiveness question here from Triton versus Torch End?
For Triton versus Torch script. So I think, right? Yeah. So well, okay. So first, they have the exact. So I'm using the exact same EC2 instance here, right? So G4DN. So the cost per hour is exactly the same, right? Now the cost per inference is dramatically lower, right? Because well, you're gonna have like 15 milliseconds versus 126, and also you can use all the goodies coming with Triton, which, as I said, are dynamic batching, right? For instance, right? So if you tell Triton, hey, dude, I mean, if you get 10 images coming at the same time, batch them together, right? Triton's going to do that, right, for you, and that means that it's going to exploit like the GPU out of the box, right? Whereas for Torch script, you cannot do that. I mean, you can implement like batching yourself, but right, it's definitely not coming out of the box for a real-time endpoint.
Yeah.
So
okay.
I would say cost is effective in terms of Triton.
All right, perfect. Yeah, in the interest of time and for our next speakers, let's wrap it here. Francesco, if you're staying online a little bit, you can maybe answer the additional questions. I see one more here in the chat. Maybe
sure, absolutely.
in the chat. Yeah.
Thank you guys. Thank you guys a lot. Thanks a lot for having me.
Thanks so much, Francesco. Great talk. All right. And with that, hand it over directly to Joe and then Daiming, who will, in the spirit of Torch, keep it going, of PyTorch, and show us a new native integration with S3. So Joe, if you want to jump in.
Sure. Thanks, Antje. And thanks, Francesco, for the amazing demo. So hi, everyone. I'm Joe Evans. I'm here with Daiming Yang. We're both from the Deep Engines tools team at AWS. Today, we wanted to show you some work we've done to incorporate an S3 data plugin into the public PyTorch ecosystem for loading model training data. We originally announced an open source S3 plugin for PyTorch back in September of 2021. But we wanted to contribute this functionality to everyone in the PyTorch community and make it accessible natively in PyTorch. So Daiming actually recently finished contributing this functionality to the Torch data package, and it's present in the new PyTorch 1.12 release. It incorporates portions of the AWS C++ SDK to get the best performance out of it. And yeah, today Daiming is going to give a short demo on how to utilize it. And then we'll leave some time at the end for questions and answers. Daiming, you want to share your screen?
Yeah. Hi, everyone. So this is Daiming. I'm going to present the new S3 data pipes inside the new Torch data package. So this is documentation on the S3 plugin. Inside the Torch data, it has all the information you need to build from source, or it has links to the examples, and there are a few things that you may want to troubleshoot. So we have all these listed out. Meantime, so we did provide, as Joe mentioned, we did provide Amazon S3 plugin for PyTorch. That was to give users a better user experience by saving users time to save their energy and save their time, because as everyone knows, PyTorch or TensorFlow is a little difficult to write your own customized data set, and it's even more difficult to stream data from S3. So we write those data set for you, so you can just directly use those data sets and no need to write your own. And with the new Torch data, which is a very amazing project to rewrite the entire data set logic by using a series of data pipes as data flows from inside these data pipes, and then you generate all the data and get flush all the data into the data loader. And now with so each data pipe has its own functionality. It focuses on only one thing, either it's streaming data, listing files, load files, or like extraction from a CRV for CSV or from TARS. And for S3, we introduced the two new data pipes are S3 file lister and S3 file loader. And they're pretty simple. I'm going to introduce you. Now, like you can see this short code snippet, that's all you need to do for loading data from S3. This basically, first of all, dependency, we need the latest Torch or Torch data and Torch data. So pip install those two packages. It's pretty simple, right? And then we just, in our Python code snippet, in our Python code, we just need to import these two data pipes. One is S3 file lister, one's file loader. Here, I'm going to have a simple demonstration. So here I'm using this shared tar shards, which I had, and it has 10 shards. Each one is about 1.5 gigabyte. And then simply you list the files under this bucket, and then you load the files given all the listing, given all the files listed by the lister data pipe. Then the loader data pipe will give you pairs of the URL and then the actual file data. So file data, you can call file data the read, and then here just print. So I printed it like I run it before, so to save us some time. And from there, if you are not satisfied with the file data itself, you can keep going with other data pipes to read the data. You can, as you can see, it's very simple. The data pipes has a very simple analogy. And then to give you some idea on why we want to use the new S3 data pipes. So our S3 data pipes are 23% faster than what we call, so we're using the CPP, AWS CPP SDK on the backend, while AWS S3, the AWS CLI, and which uses Bodo 3, which is the AWS Python CDK as backend, we're 23% faster than that. and giving an idea of the put into real numbers is about 250 megabytes per second versus 200. But noticeably, I did this test with the large files. This was 1.5 gigabyte. And however, it's noticeable that S3 data pipes are not that fast with small files. But for small files, we're getting much slower throughput, which is only 3.5 megabytes per second. So I did this test on the P3.8 X large. So to give you an idea of the comparison on the throughput. So given this performance comparison, I believe users should choose their data pipes intelligently based on their own use cases. And one other note would be the file lister is only necessary if all the URLs are unknown before. It's always faster to generate these URLs locally. Like if you have a logic behind all the naming, you can just generate all the file URLs locally. So also, this new data pipes is actually much faster than the original S3 plugin. So during importing from the original S3 plugin to the Torch data package, we have optimized it. And it's given the use cases, the speed is faster by 15% and even up to 10 times. So that's 1,000%. And another one will be actually coming from the Torch data itself. Before, it should be well known that to write a customized data set is very difficult. But now with the new Torch data package, everyone can just use a series of data pipes, and each data pipe focuses on one little functionality. And all the data pipes will have all the data flush from the upstream to the data loader. And this Torch data with the S3 data pipes plugin is, first of all, available in Torch data natively in 0.4.0 and together with the Torch 1.12. So it's actually already innate in the Torch data package. Installing these two packages, you will have the S3 data pipes functionality enabled. You don't have to install, for example, AWS DKCPP yourself or any other dependencies. It's also available since actually in the PyTorch 1.11 DLC containers, which we first introduced these two data pipes, and it's upstream into the Torch data in the 1.12. But we have on the A-level side, we have it enabled in the PyTorch 1.11 version already. So that's very quick and short introduction to this new S3 data pipes. I can take a look at all the questions you have now.
Great, thanks so much, Joe. And I mean, I'm really excited to start using this plugin here. Question coming in, is Torch data compatible with large Parquet files?
So it's just loading data. So there's nothing about whether the file format. So you load the file locally, you stream the file locally, and you do whatever you want. As long as it's stored on S3.
Gotcha. Another question, can you elaborate on generating S3 file URLs locally versus at runtime?
Yeah, so my point at that is, for example, given this example, we have 10 tar files, and then we're using S3 file lister, and we look for that bucket and we list all the files under it. So we're generating all the file URLs at runtime. Meanwhile, you can have a for loop yourself and then generate. You have the prefix and you have numbers and from 0 to 9, and then you have a suffix. So you can generate all these file URLs yourself. Like for 10 numbers, 10 file names is not like that comparable. But if you have like 10,000 files or even 500,000 files, you can generate all those. If all the file names are in order, you can generate them yourself through Adorator.
All right. And I think, a question coming in, if you can elaborate a little bit more about the role of each module, lister and loader, what they're doing.
It's more about the philosophy behind the Torch data. So Torch data has all the data pipes. So it's rewriting all the data set logic. So we're now using the rewriting one data set and has everything under it, and rewriting, for example, the length function, the iterator function. Now it has the philosophy behind it is you're using a series of data pipes. So it's like water flowing through the data pipe. The data is water flowing through pipes. The data is flowing through the data pipes, and through each data pipe, you are doing only one thing. And the file lister is listing files, as the name suggests. You are listing files given the prefix or the path. And then file loader is actually load the file given the URLs, the file URLs. Yeah.
Right.
So
yeah.
I think I do see the links to this sample. So this is a simplified sample. So I have two links here, but you can actually find them here. So under the i3.io data pipe documentation, you can see here's the example. So that's a more comprehensive, as in you can use the file lister, or you can actually use a functional API, which has a more meaningful name. You list files by S3, and also lists out all other arguments that you can set. For example, you can, if your data set, your S3 bucket is on a different region, you can specify that.
All right. Another question around the performance. Is the performance improvement different for different data types? For example, video, images, CSV, text files, etc.
Oh, so that's actually all related to the i3 data pipes themselves. i3 data pipes, you're just streaming data. You still need to post-processing after you have the data locally. You still need to process it, and you can handle it by writing your own data pipe. Or if there are existing data pipes that can handle those data, for example, images, you can use those data pipes already. So for any data pipes, for any data types, it's just loading the data. It's the same for the i3 data pipes. They're just data itself.
Yeah, and maybe we need to clarify a little bit the term data pipes, right? So yeah, Chris, you had a question. Is the idea behind data pipes that you can chain together many pipes?
Yes.
Maybe you can give other examples of, yeah, useful data pipes.
Yes. So it's more about, so it's composable data loading. So this will give a better clarification on the data pipes. So data loading now so data loading now is you're, for example, have a HTTP. So given the URL, you're reading the URL, then you parse CRV, and then you batch them. So, or this could be, let me see. Yeah, they didn't provide a better example, but the basic logic is, yes, you can create a DAG of data pipes. So data flows from the upstream where you store the data. And with each data pipe focuses on one thing, either listing or loading or processing, then you get, or further processing, then you get the actual data types and the data shapes that you want. And that these data, after all the processing you've done, will get into the data loader for training or for inferencing.
Okay. And then, yeah, just to clarify another question, you mentioned it earlier, the recommendations when to use. So for small file sizes, it's better to use AWS S3 Sync. Just, yeah, clarification here, because you mentioned like the small file sizes and the larger ones, which one to use?
Yeah, so if it's really small files, like very tiny images, AWS S3 Sync will be faster, but as I also indicate here, the throughput will drop from over 200 megabytes per second to only 3.5 megabytes per second. So do choose wisely.
All right. Yeah, follow up, I guess, on the Parquet question, because Parquet, is a very popular format. And I think historically PyTorch didn't support Parquet and only handled the CSV files. Do you know, does PyTorch now support Parquet?
I'm not sure about that. So because this project only focuses on like streaming data, and post-processing is not related to this project itself.
Yeah, okay, so we have to double check on that one.
Yeah, thank you.
Yeah, no worries. Any more questions here? Let me see. Chris, do you see any more questions coming in on your side?
I don't think so. I think, yeah, this was really good. Sorry, there's a plane flying above me here. Yes. Right, so, okay, that's interesting that you can construct a DAG. I actually didn't realize that. I know we had spoken internally leading up to this event, Daiming and Joe, but and because with a lot of these training jobs, we see it's really the data ingest that's the bottleneck, right? And trying to saturate these large accelerators. And so this is a step in that direction. This is a very big step in that direction to speed up. Is there any way, I guess, to like detect where there could be bottlenecks? Like, does this new Torch data pipe concept give us any tooling to highlight where we could improve on the?
Yeah, I don't think there's a tooling yet. We have to, for any user, he has to, first of all, it's based on the use case itself, as in if the files, first of all, I think this data pipes is usually used for training only, because inferencing is usually the small files. And on the other side, it's usually because the files are too large to store locally, or there's a bottleneck, or anyhow, the data itself is too difficult to store locally, and we have to pull it from S3. That's why we want to consider using the S3 streaming data pipes. So, and regarding the performance wise, why we're using this, and is there any tooling to find the bottleneck? There's nothing yet. So we have to conduct the experience ourselves by use this or other tools and see if the training performance actually is gained or lost.
Gotcha. And I just proposed kind of a question because it looks like Francesco's still on here. Francesco, do you have any comments on this? Like, would this have sped up your training times?
Potentially, yeah. I mean, it's in my case, honestly, I generally try to work with as little data as possible. So I don't think that probably that would matter a lot, like in my case, because I literally, the use case which I showed is trained on 1,000 images. So it's 300 megabytes, right, of like all of it. But yeah, so totally, like it's a game changer in terms of like when you have like to get like a lot of data into a training pipeline.
Yeah.
Right, because you were pulling like images from S3, right? I believe.
Myself, you mean?
Yeah.
Oh, no. Like I was like in like the training is happening directly inside like the EC2 machine. So like I'm literally just downloading like this data set from GitHub,
Gotcha.
and everything is happening locally. Yeah.
Gotcha. And right, because SageMaker actually copies the data down into those.
Yeah. But totally. But yeah, I mean it's a good point. So like to avoid confusion, I'm not training with SageMaker, with the SageMaker SDK, right? I'm literally just training inside the notebook locally, right? So I'm not actually using.
Right. That's right.
Yeah, I'm not using the SDK like to train the model. Your point is definitely completely valid if I would have used like the SageMaker SDK to train the model.
Gotcha. And yeah, Daiming and Joe, potentially, you know, how are we supposed to use this within SageMaker? This actually, so I just mentioned that with SageMaker training jobs, there's some behind the scenes magic where these data sets get copied when you launch the training job. And this actually negates the need for that, right? So we could potentially just point to S3 within our code, and that'll speed up training times because we're not waiting for the copy to happen, and actually cleans up the code a little bit, makes it a little bit more like intuitive, right?
Yeah.
Just go straight to S3. Gotcha. And we do have something within SageMaker called fast file mode, and of course pipe mode, and some of these streaming, you know, I call them secret sauce, but you know, yeah, they're not so secret, they're all open source. But the ability to do something like this, streaming data, but I like this because this is directly you know, debuggable and grokkable, and I can profile this directly from within my code without having to, you know, rely on some of the SageMaker profiling tools and things. Okay.
Yeah,
Very
also,
cool.
other than the SageMaker use case, anyone who uses CC2 or just want to train themselves on their local machine, they can still use this. It's all open source in the PyTorch world.
Right on, right on.
Yeah,
and it's
yeah. Go ahead.
Yeah, Antje, go ahead.
No, just the one question here, if we have like a very good use case, like the sweet spot use case, like when should you definitely try this out?
Yeah. So I mentioned basically, first of all, it's usually only used for training because for inference, it's usually small files, which they're just new files, new data, and they're usually kept small. And on the other side, it's the reason why we want to use the data from S3 firsthand is because there's difficulty to use them locally. So at that time, that will be a use case for the S3 data pipes.
All right. I think if there's no other urgent question coming in, it's a wrap. And with that, yeah, thanks so much again to our speakers today. Thanks, Francesco. Thanks, Joe and Daiming.
Thank you.
Great insights here. And everyone, thanks for joining. And feel free, if you're trying out those tools, let us know any feedback. We're super excited to hear from you if you have anything to share using those tools.
And
Thank you very much. Thanks.
Yeah, we'll post to the YouTube channel.
The recording will be posted to our YouTube channel coming up in a bit. And feel free to join us next month too. Thanks, everyone. Have a good day.
Thank you. Bye-bye.
Bye. Bye.